Then we'll move on to the last talk of the morning, which is by Lionel Naccache, who's a professor at physiology at Sorbonne University and a professor of neurology at Pitié-Salpêtrière Hospital. Co-leads the picnic lab with my friend Laurent Cohen at the Paris Brain Institute. Lionel is, I think, one of my first, maybe the first.
I think the first inscribed and the second defended.
Okay, first PhD student in my lab, so it's quite, it goes a long way. Okay. And we did a lot of study of non-conscious processing together, wonderful PhD, a Nature paper. And then Lionel is a doctor, and he came back to real important stuff, which is to help patients. And we discussed that, I remember very well. And we said, well, wouldn't it be wonderful if you develop the science of consciousness in the neurology world to actually help patients detect conscious versus non-conscious states, bring all of the tools of imaging to these patients. And that's exactly what Lionel did, so it's absolutely fantastic.
But the story is not over.
And it continues. Yes. So thank you, Lionel. He's going to talk about exploring consciousness at the edge, Global Neuronal Workspace Framework, and neurology. Thank you.
Thank you very much. Thank you very much to everyone. So first of all, of course, I'm extremely pleased, like I think all the speakers, the participants, the audience, and the colleagues, to be here and to celebrate the absolutely outstanding scientific achievements of Stan. And as I said, it's not a ended story, but still the story is rather incredible. And of course, so I even used new slides. As we know, one of the most impressive aspects of Stan is his ability to monitor and to enter into so different fields of cognitive neuroscience. And the Hilbert-inspired list of problems of this morning is a good illustration of that. And so today, this morning, I will only address one aspect, which is consciousness. But of course, consciousness is everywhere, in a way, we could say, as a question, implicit or not. And so I will just allow me just one self-related episodic memory or autonoetic memory storytelling slide. So rewind back in 1995. So in 1995, I was looking a little bit like that. So I was a resident in neurology, young neuroscientist. I was working at the Salpêtrière, and I could meet with Laurent Cohen, who is a very close friend, colleague, collaborator of Stan. And Laurent is one of my two mentors with Stan, and Laurent, I consider him as my mentor in cognitive neurology, behavioral neurology. And I told him, I would like to work on consciousness. I read a lot of things about, and I had a lot of ideas or questions. He told me, you have absolutely to come to one of the lab meetings, to this fabulous lab at Maison des Sciences de l'Homme, Boulevard Raspail, the LSCP, Laboratoire de Sciences Cognitives et Psycholinguistiques, headed by Jacques Meller, of course. Stan evoked his memory, and I could finally meet Stan. And so really there was, it's not a storytelling really reduction of complexity narrative. We met one day in the afternoon in 1995 after a lab meeting. I said to Stan, I want to work on consciousness. Immediately we discussed together. At this time he was, of course, interested by consciousness, but mostly working on numerical cognition. So he told me something like, let's make a deal and let's study conscious and unconscious perception of numbers. And so that's the way the story began for us. So let's explore consciousness together, and we are here 30 years later. So I will try to really address the way you can use Global Neuronal Workspace Framework designed by Jean-Pierre Changeux, Stanislas Dehaene, Claire Sergent, myself, and colleagues, how you can apply it and use it to neurology and to special cases of neurology in the clinical practice. And of course, there are two goals, very obvious. First, you want to use neuroscience to help patients and their relatives, and it's far from being easy and useless. It's very important to try to do that, improving diagnostic and prognostication. I will show you that. But also trying to improve the way we can take care and therapeutics by understanding the physiopathology. But also, of course, as you know, there is a reverse direction goal. Patients, really, it's absolutely true in our field. Language, memory, consciousness, whatever. Patients do enrich scientific theories of cognition and their biological implementation in brains. First, because they illustrate extreme and very unusual dissociations or conditions that you may have difficulties to imagine, and to be able to discover new concepts that you can then generalize back to normal cognition, let's say. And also because of the lesions, you have some causality argument that you can make from patients. So it's really important. We try to explore very different aspects, but I will do this morning only, maybe you will be frustrated, but I will only explore what is called disorders of consciousness, lasting disorders of consciousness after a severe brain injury, cardiac arrest, traumatic brain injury, and I will go on this aspect. So I would just like to begin by a very brief introduction to this Global Neuronal Workspace framework that was also presented this morning by Peter, by Stan, etc. Just to come back to a very few ideas, because you know nowadays the model is stimulating a lot of words, a lot of discussion, so emulation and contradiction, so that's really important to go back to it. So first, I would like to insist on the fact that it's a framework. We put it as a framework, not really a definitive theory, but a theoretical framework, which is driven by cognitive psychology. So our work is to go to the brain, but our initial inspiration is cognitive psychology of consciousness, and we use the following criterion that was mentioned: self-reportability. Considering that an individual is conscious, this individual can self-report any mental content to himself in a first-person perspective. Self-report is not a behavior, so we use the word reporting, self-report, but it's an internal process. Of course, you can use behavior to communicate it, etc., but the self-report is not a behavior. It's not necessarily verbal. You can have non-verbal self-reports. I don't have time to discuss, but if you have questions, we can discuss about that. And once you put things this way, you use this criterion, you have to ask two questions. What are the brain requirements to be in such a conscious state to be able to self-report anything? And then the second question, if you consider a conscious individual, so an individual in this state, what are the brain mechanisms allowing that you are conscious of a specific content, the conscious access question. So these are the two questions we try to explore. And the beginning of this model is the fact that when you turn to cognitive psychology, and using this criterion, you discover that you have some cognitive properties which seem to be specific to the consciously accessed representations. So it's a very long story, but one, and it's a field of research by itself, but one of the key properties is this one, this notion of cognitive availability, which was put forward also by Bernard Bass initially, the cognitive psychologist Bernard Bass. And basically the idea is that we could discover a lot of very clever unconscious processes that you cannot self-report. But it seems that as soon as you have this self-reportability property, that you are conscious of this information, this something becomes immediately available to all other high cognitive level faculties or processes, as if you were entering into a new cognitive space. A non-modular space, if I would use the Fodorian terminology, you have modularity of a lot of unconscious cognitive processes with all the criterion of modularity, encapsulation, with close to automaticity, encapsulation, fast, difficult to exert executive control on it, but very encapsulated, very domain-specific. But it seems that when you are conscious of something, you break this modularity, and you enter into another form of cognitive processing, which is not restricted to modular organization. And what we try to do with Stanislas, with Jean-Pierre, with Claire, is simply to find the single axiom of the theory, I would say to propose that there is a neural equivalence to these cognitive properties. So we should predict that when you have unconscious processing, you would have, neural modularity of many. And when you are conscious, you have neural non-modularity. And the workspace ISD is a way to take into account these two modes of processing. So let me illustrate briefly. Long time ago now, we used subliminal processing, like Stan said, and we showed, for instance, that when the word is subliminally presented, you cannot self-report to yourself. Still, it can be processed, and we were the first to show that, for instance, you can activate the ventral pathway by subliminal words, in particular the visual word form era that we label with Laurent, with Stanislas, with Stéphane Lerici and colleagues. And, but still, when you perceive the same word, but this time you perceive it consciously, you can self-report the word. Not only do you have this focal or modular system which is activated, but it is also co-activated with a brain scale network implicating high-level regions, prefrontal, parietal regions in particular, in the specific case of conscious reading network. So the basic idea of this schematic figure inspired initially by a Mesulam paper that Jean-Pierre and Stanislas and Michel Kersberg used. You have concentric circles. The most external correspond to cortical regions close to the periphery, to the external world, so the primary cortices, visual, auditory, somatosensory, motor, etc. And the more you go inside, the more you climb into the hierarchy of the cortical organization, all the way up to high-level processors. And basically, the proposal is that at any time, so you have specialized networks connecting processors located at different levels of the hierarchy, let's say word reading or whatever. So, but they have a very modular and parallel organization, and all that stuff would process non-consciously. It could perform a lot of very clever things, but it would not access your conscious scene, let's say. But you would have this high-level, very interconnected network. That would be the core global neuronal workspace. And this network, when something is broadcasted in it, you would have this global availability process enabling you to process it with all your, let's say, faculties that you are able to process. And when you do that, so if you remove the workspace, you would have, let's say, the space that would correspond to massive unconscious processing, but also it would explain something which is famous also. We could say the price to pay to be conscious and to have global availability is that you could be conscious only of one thing at the same time due to the high intraconnectivity organization of this workspace. And that would be our explanation for like the bistable figures, the Jastrow, rabbit, duck, of course, that at one point, at one moment in time, consciously, you serially alternate between different all or none content. You cannot be conscious of the two meanings at the same time. And it's not because we are at the Collège de France or in Paris, but we like to cite Descartes, because when you cite this sentence of Descartes more than 250 years later, it's striking like a plagiat of the global neuronal workspace. We have only one thought of the same thing at the same time. Okay, so we try to give account of this process. And like Peter also reminded, we proposed the mechanism by which you can amplify something located outside the core workspace. It was developed a lot. So it means that you have dynamic fuzzy frontiers, like when this morning Peter showed that you can have conscious access signals in V1 or in other areas. It's not surprising according to this top-down amplification of regions that can not necessarily contribute to conscious processing all time long. So I'm almost done. I will skip that for sake of time. But basically, you have these two times of perception that Peter also reminded. You have a fast feed-forward sweep crossing all your brain areas during perception, which is not conscious before this broadcasting, conscious access, ignition. And you have the second stage characterized by the increase of connectivity, functional connectivity between global workspace components and the corresponding areas or networks, which will be amplified. And with Raphael Gaillard, for instance, we could show that. So I will move to patients now. I'll skip it. You move to patients, and in particular, you have this category of patients after a brain injury who can, so there are the comatose state in which the patients are not awake. So the vigilance arousal systems are off or are very impaired, and the patient is not aroused, not vigilant, not awake, but also not conscious. But the most difficult part, I will not sleep of comatose except if you have questions, but we have this kind of two states I would like to focus on this morning. You have some patients who, after several weeks or months of such a comatose state, can turn to a strange state in which they can recover vigilance, at least sufficient to keep eyes wide open during hours without intense deliberate stimulation of this patient. But still, some of these patients do not seem to have conscious experience, as you can say by behavior only. So it's called vegetative state. I will not discuss the terminology, which we can discuss, of course. I will not. And the other one are these patients who cannot engage in functional communication. As soon as you have functional communication with the patient, you can collect subjective reports. The patient is labeled as conscious or emergence from minimally conscious state. But still, you have this state in which the patients show signs are reminiscent of conscious processing in many aspects, and I will go back to this point. So the first thing is that you want to focus on this kind of minimal contrast in which, with the same level of arousal, approximately, you can have one category of patients who do not seem to be conscious, whereas some others seem to be conscious at least some of them. I will come back to that. And for this minimal contrast between VS and MCS patients, if you turn to the global workspace theory, you would say, okay, if you are awake but not conscious, the framework predicts that the lesions of your brain should be located not in primary areas or secondary areas, but mostly in the frontoparietal network and the corresponding thalamic regions interacting with this network. And one of the first key results for me is this fantastic result by the group of Steven Lorace in Belgium 20 years ago, in which they did exactly that with FDG PET, so metabolism of fluorodeoxyglucose PET imaging between two populations of patients, VS and MCS. And what you see is that the only regions which differ in terms of metabolism are not brainstem or cerebellum or primary areas. You really tap onto, let's say, a picture of a workspace-like framework, high-level hierarchy system. So it's a first way to try to test some of the prediction of the framework in these patients. And then I go back to behavior. So the way we test these patients, a lot of neurological examination, but also a lot of, let's say, behavioral observation beyond traditional scales. So one of the scales, which is really the gold standard, it's called the CRSR, so Coma Recovery Scale, the revised version by the group of Giacchino, which is, to put it clearly, it's a fantastic scale for many reasons, very reproducible, very easy to learn, and so the tool is fantastic. And to be able to distinguish VS from MCS is super important in terms of diagnosis and prognosis of patients. So there is no discussion about that, okay? I think I put one slide, a work with Frédéric Faugeras. Survey analysis, patients with MCS are more prone to survive than the other one, and it's not only self-fulfilling prophecy to have a withdrawal of active care for the VS. It's not only that. And when you have the follow-up of living patients, the proportion of patients who can recover overt conscious behavior is much more important in the MCS than in the VS, and many studies publish that. So there is no discussion. To be able to distinguish MCS from VS is super important. Then one of the questions is, what does it mean, minimally conscious? You see that the expression is problematic. We say minimally. So what is minimal? In French also, you know, the adjective is relative to the gender of the noun. So you can, when there is a newcomer, I just pay attention. How will he or she write état de conscience minimal? Minimal with a E, so the consciousness is minimal, or état minimal without E, so the state is minimal. So it's really messy. And so I wanted to go back to that, because according to the scale, it's a subscale with different apparatus. For instance, if a patient does have visual pursuit following a mirror, you would say the patient is not VS, he is MCS. So this single item is enough to qualify the patient as being in MCS. And I told you MCS is super important to recognize, but I don't think it means MCS. That's the point what I want to make. And in a brain paper a few years ago, I just listed here for the different subscales, the green items are the items corresponding to minimally conscious state, and the red items correspond to vegetative state. And what is really clear, I just illustrate with the auditory function. When you clap into your hand intensely, like, so some of you will have an eye blink, that's the auditory startle response. So if you have auditory startle, it's not a MCS item. But when you see the neural circuits located, it's in the brainstem, it's very well characterized, so you need only a brainstem to have auditory startle. The same for localization to sound. We can have cortical evidence too, but Oliveri complex in the brainstem computes the oral, using the oral delay between the two ears to have a left-right localization of sound. So we know that a basic left-right localization is not enough. So actually, it's used as a VS item. And when you move to reproducible movement to command, then the patient would be labeled as MCS. And what you can see is that in this case, you need cortex here. To have this green item, you need cortex, and I will not do the same for all the other items, but what you can see is that as soon as one of your items is supposed to be MCS items, it only means one thing. It needs that by simple behavioral observation, you see that there is intervention of cortical networks in the behavior you observe. But that's nothing more. So in a way, minimally conscious does not mean anything about consciousness. I don't think so. But if you want to keep the letters, of the acronym minimally conscious state, I propose to make an anagram of the acronym to propose CMS for cortically mediated state, and which is a huge difference. So when I use this scale, I cannot say the patient is conscious or not, according to the definition we have and to the behind subjective experience that we share. But you can be completely 100% sure that some cortical networks play an overt role in the behavior. And of course, the more you would have preserved cortical activity, the more you would be prone to be conscious or to recover consciousness later on. And it also means, so it's really important for ethical aspects, because discussing with the family, when you say minimally conscious, you say conscious. But you have some patients who will have only the visual pursuit without any other sign, suggesting that they are conscious and who will not recover. So I think it's really important to be clear on the concepts and the evidence we have behind. And it also means that you need to go beyond behavior to probe consciousness in this patient. So you need behavior, but you need to go beyond. So for instance, with Bertrand Herrmann, to test this idea of CMS, we just use PET imaging, and we contrast VS-MCS patients, but only according to each item. So for instance, here we contrast visual MCS versus the patients who are not visual MCS. According to the workspace, if you are conscious, the contrast should delineate a workspace. But if it's only a CMS item corresponding that you only probe visual circuits, you would see what we observed, that the only regions which were more active in metabolism in VS, in visual MCS, were only the occipital regions. The same for somatosensory MCS items. But when you move to auditory MCS, I remind you it was response to command. Here, not only do you see auditory areas or language-related areas, but you begin to see a workspace-like network with precuneus, prefrontal, parietal. So what I mean is that MCS is super important to recognize, but it's a very diverse, heterogeneous population of patients. Some of these patients may be conscious, some are most probably not. So let me illustrate you, because the way it works, it was the story of one patient, a 25 young patient, after traumatic brain injury and fat embolia. I will not describe the case, but he remained in comatose state for more than 2 weeks and then moved to VS. UWS and VS are synonyms, so vegetative state. And then after more than 1 month, he could emerge to MCS and then to consciousness. But the reason why we reported this case is because we were called to evaluate this patient during this period. He was clinically VS according to the CRSR, but we could find evidence that actually the patient was most probably in a higher state than the behavior was showing, and we predicted that the patient should recover consciousness, and that's what happened. So what we do? We use a lot of EEG, for instance, high-density EEG, and with Jean-Rémy King and Jacobo Sitt, close colleagues and friends, we began to test some properties of, and with Stan, some properties of the workspace in these patients. For instance, we began by saying, okay, in conscious controls, you should have, if you have a workspace working, you should have long-distance cortico-cortical connectivity, functional, which is working. And that's what you observe here. It's a new metric that was designed by Jean-Rémy and Jacobo, the WSMI, Weighted Symbolic Mutual Information, that I will not describe now, except if you have questions. And when we tested the patients, you still find the topography in conscious individual, but patients, so they are ill, they are in hospitals, etc. When you move to MCS patients at the group level, you still see this general pattern, but you have a massive drop of functional connectivity, cortico-cortical, long distance, in the VS patients. So it's a way to probe one of the predictions inspired by the workspace to probe workspace activity through functional connectivity, cortico-cortical connectivity. The same in terms of topography of this connectivity, I will not develop. Early on with Stan, we insisted on the importance of complexity, like developed by Giulio Stononi and Jerry Edelman at this time. So the fact that conscious access or conscious ignition into a workspace, it's not an epileptic seizure. It's not that all your workspace reduces its complexity to do only one thing and you are not conscious. And actually, with my colleague from Marseille, Fabrice Bartholomé, we could demonstrate that actually when you lose consciousness during epilepsy, there is propagation of the seizure within the workspace, and there is this dramatic decrease of complexity. But when you are conscious, during conscious access, you still have highly differentiated and highly complex components of the workspace. And so we can measure that at bedside. And again, with the same team, we could report that the complexity Kolmogorov, spectral entropy, permutation entropy in the theta band, you have this decrease. I mean, you still find some complexity, but you have this drop in VS patients. And one thing is that you can use all these kind of markers together. I saved you a few markers. So we could combine in this brain paper in 2014, you use a basic machine learning algorithm, and it was an SVM initially, and then a random forest in the second study, in which you train your SVM with a database of patients that are well characterized, either VS or MCS, okay? And so now you can have two things. You have your clinical behavioral diagnosis, and you can complement it by the trained EEG algorithm to have the classification of the algorithm based on your database that you train it with. And one of the first results we had, which was very encouraging, you have here the result for the first 75 patients who were clinically, behaviorally well-defined VS patients. So for us and for our team, you repeat the CRSR, etc. These patients were in the vegetative state. So then we turned to the EEG algorithm, trained with these measures, inspired by the workspace. And what we saw is that actually, if 2/3 of them, 50 out of 75, were classified as VS by the EEG, 1/3 of them, which is really a lot, were classified as being at least in MCS or better state. So what we did is we just waited and observed the follow-up and the outcome of the patient, and 6 weeks later, the proportion of patients who progressed from VS, clinically VS, to MCS or higher was double the proportion you could observe in the VS-VS group, meaning that you can capture something which is difficult to see with only the behavior. So highlighting the importance of using such tools or related tools. We could show with Denis Engelmann, Federico Raimondo, that you don't need 256 electrodes, but only if you subsample to 8 electrodes and to 1% of the recording. So in the end, it's 1% of EEG that you have in any intensive care unit. Actually, the AUC, the performance of classification, moved from 0.77 to 0.74. So actually, you don't lose that much. So it can be used in daily practice, not only in expert centers, to add and to provide these measures. We also designed, even before this time with Tristan Beckenstein, this local global task. I will not develop it today, 26 minutes. But basically, we wanted to have a task to disentangle between the feed-forward sweep of auditory processing from the conscious access. And to do that, we based on detection of regularities of the auditory structure, either local in-time regularities that you could perform unconsciously, which does not require working memory, that's the local effect, intra-trial novelty, or inter-trial novelty, global novelty that requires you working memory, elicitation of the regulation, detection of the regulation, a lot of things to combine. That's the global effect. And to make a long story short, we could show that you can measure mismatch negativity and P3A for the local effect. It's coming only from the auditory cortices in fMRI, and with epileptic patient implanted electrodes, you have intracranial MMN here signal. And for the global effect, nicely, it was a late time window, as we predicted. It was not restricted to auditory areas, but to a large, including frontoparietal areas, fMRI, intracranial EEG. And in healthy volunteers, you see the global effect only if the subject, at the end of the experiment, can report you that he or she was aware of the global regularity. If for many manipulations that we can make, that you can imagine, the individual could not access to that, he will not show a global effect. Since then, we turn to the patients, Frédéric Faugeras, with Benjamin Rowe. We have three really main colleagues at the Salpêtrière, Jacob Ossid, Benjamin Rowe, and myself on this aspect. And with Frédéric Faugeras, we had the first two patients with a global effect who were VS and recovered, moved to MCS and EMCS 3 and 5 days later. And since then, we know that global effect so far has a positive predictive value of consciousness recovery in survivors of 80%. So we consider it's a very exigent term. If you do not have a global effect, you cannot say the patient is not conscious. But on the reverse, if you find a patient with a significant global effect, you have to raise questions if you consider the patient as not conscious. You can use pupillometry to do that. I will skip. And more recently, you can use same kind of machine learning algorithm. The group of Yann Claassen, Benjamin Rowe, and I think Jean-Rémy was part of this story too. You can use the same kind of approach to detect response to command during response to command paradigm. And recently in the New England Journal of Medicine paper, we showed that up to 25% of patients who are considered as unable to respond to command overtly show a better than sense level detect classification rate in these stats. We can discuss, of course, the interpretation of that. So we move to structural brain imaging. We are convinced that to do that, you have to develop new behavioral tools, but also to explore a lot of facets of probing your workspace. So we use diffusion tensor imaging, as you can see here, and the group of Lionel and Louis Pubasset showed that you can predict consciousness recovery according to the importance of the loss of anisotropy in these white matter bundles, delineating long-distance cortical connections. And we did a more recent work with Victor Altmaier and Benjamin, in which we could show that there is a correlation between the functional connectivity as recorded with EEG, WSMI, and with the DTI, MRI fractional anisotropy, so a correlation between structural and functional connectivity in these patients. And most interestingly, when we restricted the analysis to the white matter bundles that were specific to the workspace, not all of them, we could even increase this connectivity. So we use this measure at bedside. We use PET imaging, fluorodeoxyglucose imaging, I told you. We use it in patients who can have this recording. And I would like to show you two things. I'm almost, it's okay. So we have to develop new clinical signs. And I showed you just one of these. We have 3 signs like that. So like 20 years ago, I observed, so when you do the CRSR, I told you, you look for the auditory startle. So you clap in your hand. And I observed 2 kinds of behaviors, like this one. I don't know if you listen to anything. Okay, so you have, sorry. Yes, I play it again. It's not long. So you have this kind of behavior. So you see that there is no habituation of the startle. Whereas the second movies I showed you, I sent the one you showed, you saw, you had auditory startle to the first stimulus or to the first 2 stimuli, and then there was complete extinction, inhibition, habituation of this reflex. And so our idea was maybe that actually with this basic sign, when you have extinction to auditory startle, that would mean that you would still have a kind of working memory of preserved workspace, detecting and anticipating the next stimulus and inhibiting the reflex. And that's what we tried to test on a large population of patients. And first, we saw that patients with this new sign, most of them are in the MCS group, according to the items of the CRSR that do not include this new item, okay? Second, even this item ranked second about the performance of each individual item of the CRSR to recognize MCS patients, behavioral MCS, which is not trivial because all the other ones there is some circularity. They contribute to the scale. So, okay. And then when we use the EEG, the patients showing this sign have much higher long-distance connectivity, EEG, with the WSMI. They are more often classified as being VS by our machine learning EEG algorithm I showed you. And you see in particular, in blue, so you have the mass striking effect, and you can disentangle between the clinically VS, a clinical VS patient with this sign will be very often classified as in the MCS group. And in PET imaging, we discovered that patients with this sign do not have only higher metabolism in auditory, but really in a workspace delineated network, frontoparietal thalamic network. So we use this new sign. And you know, now it's validated as a new sign. And it's very easy to train people, and you can test it in any clinical unit. We have other teams. I showed you a story. A patient referred to us with, after a traumatic brain injury, CRSR scoring 13, so he was MCS for the auditory. He had the auditory startle extinction I showed you. He had a global effect, so suggesting to us that the patient was most probably conscious, even if we could not confirm it through behavior. The motor response to command with EEG was significant, with an AUC, a significant AUC of 0.57. He was decoded as massively MCS, so it's not something pejorative, but if we record EEG from each of us, it's not the case that all of us will reach this decoding performance. So it was decoded as massively MCS for the SVM we use. You can see the pattern of permutation entropy, of alpha posterior, alpha power, normalized power, which is also a powerful sign. We could even record his eye behavior. I showed you that. And not only the patient could really target faces, important aspect of the picture, but even read words. I mean, suggestive of reading words, you will see. And here, most probably he's reading that. And a few days after the end of the evaluation, the patient could emerge from minimally conscious state. We could discuss with him. He could go to rehab, and he could, unfortunately, like 6 or 8 months later, he had another complication and he passed away, but he could discuss with his family at this time. So we could anticipate this kind of thing. And recently, with Benjamin Rowe and Charlotte Caligaris, we published in Nature Medicine a study showing that actually this kind of approach is really relevant for the clinic. So what we did, very short, we used the outcome scale, which is a famous outcome scale in medicine, in rehab, the GOSS extended scale. Basically, if you have 1, 2, or 3, you are either dead, VS, or you are severely disabled and most probably not conscious. It's not clear. But when you have 4, 5, 6, 7, 8, you are conscious with a varying degree of autonomy. For instance, the minimal one, 4, you are conscious, no discussion. But you can stay more than 8 hours alone, but you need some people to help you during the daytime, okay? So we did this study, and for each weekly staff, we say, okay, either the patient has a good we think he can have a good outcome, or we say we think he cannot have so he should have a bad outcome, or we say we don't know. And very often we say we don't know because there is mismatch between the different metrics or measures that we have. And the result is that we see what happened 1 year later. And 1 year later, none of the patients for whom we proposed a bad diagnosis, bad outcome, could recover consciousness. So all were 1, 2, or 3 at the GOSS scale. And when there was a good outcome, it's not that all of them recovered consciousness, but more than 1/3 of them did. And of course, what is dramatically important in this kind of study, you want to discard self-fulfilling prophecy. If you say to the clinical unit, I think the prognosis is bad, the patient has a new complication, and then there is more prone to withdraw life-sustaining therapeutics, you would have self-fulfilling that the outcome was bad. So you just do the same analysis on survivors only, or in patients who did not have any withdrawal of life-sustaining therapy, and we basically observe exactly the same result. So just to say that we really need to add these tools to reduce uncertainty about the diagnosis and the prognosis, and it's also helping us to confirm some prediction. I'm done with the last thing. You can use TDCS, transcranial direct current stimulation, and basically we showed with Bertrand Herrmann in a first open label that responders, so the patient improved in terms of CRSR scoring and consciousness category by 1 session of 20 minutes long TDCS over left prefrontal areas. So the responders, 20%, it was modest improvement, but significant improvement. No one worsened, by the way, had a parallel increase of the proposed metrics of the workspace activity, so the posterior alpha, the permutation entropy, the WSMI. When you compare responders to non-responders, you see indeed that only responders show this increase in this proposed metrics of a global workspace activity for the connectivity. And you can also find new ways of testing or stimulating patients, because we discovered with the collaboration with Lucas Parra that the patient, so we could model the intensity, the electric field intensity in each voxel in a normalized space with the native anatomy of the patient, and we could see a positive correlation with the intensity of stimulation of prefrontal areas, here in red, and the propensity to increase your decoding classification in EEG. So what we want to do now is a reverse, to begin with the anatomy, with the metabolism, with the DTI, and to identify where should we stimulate this patient if they still have a residual workspace to be more prone to improve them. And just we improved conscious access signature, EAPs, and time generalization method. And with Aude Sangaré and Esteban Munoz-Muzat, we just replicated on a double-blind. The first one was an open label, but a double-blind, sham versus control, crossover design. And we have the same basic result, increase only in active stimulation, and also for the EEG markers. I hope I was not too long, Stan, but I thank you, everyone, and in particular Jacobo and Jean and Benjamin and Laurent and Stan is here. Yes, thank you very much. Thank you.